I want to talk to you briefly about the concept of this index of refraction. This index of refraction is this letter N that we will use. So let's just write that out. This is the index of refraction. Refraction. So what the index of refraction is it just essentially tells us how fast or how much light will interact with a medium that it's in. In this example that I've chosen, I've used index of refraction for air on this side and the index of refraction of water on this side. But I'm going to make a comparison here. We're going to talk about light traveling from air into water, but we're going to think about it in terms of a car driving on ice and hitting pavement and what the car is going to do. So the index of refraction physically, I guess you could think about it simply in terms of like the density of material that light will interact with. So the amount of stuff that it's going to have to interact with different waves, which is going to change its behavior. And in air is n equals 1, so that just means that it's traveling at the speed of light. So there's not much interacting with it. And here, we're like, well, something's going to happen to it, and we're going to see some peculiar behaviors. But I think we can understand that behavior if instead of doing something like this in terms of light, let's do our car example. And so first thing I want you to do is notice that this orange line here, this orange line, well, this is the normal. This is the normal, and everything that we do with light measurements and rays is going to be in terms of the normal. So the nice thing is, though, that this normal is the same gosh darn thing that we did in Physics 161, and we've carried it through to 162, and now bada bing, here we are in the last 2 weeks, and the normal is back. It is still this imaginary line that is perpendicular to the surface. So that's nice. That hasn't changed. And then here's my light ray. And I had a previous video for you to watch where we talked about the small angle approximation and why we can treat light as a line, or as a ray rather, and why that's legit. So take a look at that one. But in the meanwhile, let's think of this in terms of a car. So here's my car, and I'm driving on ice. Now it's going to happen, I'm coming at an angle, right? So one of my tires, so let's make this is the driver's side, this is the passenger side. We're in the US, not the UK, so that works. So the passenger tire is going to hit the pavement before the driver's tire does, because I'm at an angle. And when that happens, let's see what happens. I have no friction here on the ice, and then I have something for the tire to grab onto on the pavement. So as I'm moving along and that front passenger tire hits the pavement, well, it's going to grab and swing this thing towards the normal. So it's going to kind of spin it, because remember, the driver's tire doesn't have any friction beneath it. So it's going to spin it at first, and then it'll maintain an angle once it's gotten a hold. So for this thing here, if I call this angle theta, call it theta 1, well, now my movement of my car is going to bend it towards the normal. Towards the normal. So it's going to come something like this. And then this would be theta 2. Cool. So we have this relationship then between our index of refraction and the amount the light is going to bend away or towards the normal. So I can do this then in reverse. Let me draw. Do this quickly. We're going to draw this in reverse to where I'm going to go from the pavement to the ice. So while I'm drawing this, go ahead and ask yourself, what's going to happen then with my car when I go from pavement to ice? Is it going to bend towards or away from the normal? That's my normal. Let's think this through. Let's label this again. So this is my pavement. Pavement. This is my ice. So in the example on the other side, ice was n equals 1, which is actually air. And this was n equals 1.33, which is actually water. So here's my car, driving along the same angle, coming in. So I'm on pavement. I have something that's giving grip to my tires. And again, I'm going to hit here. So now my driver's side tire still has grip, but the front passenger side doesn't. Well, if I lose the friction, I have nothing that's holding that front right tire. Now what's going to happen? Well, the car is going to go this way and until it comes to a final angle and both tires are on the ice. In real life, we see this as a spin out, but if we think of it in terms of just a temporary, what's initially going to happen, then you can see, okay, I'm going to bend away from the normal, away from the normal. So my angle between my light ray and the normal has gotten bigger. So this is theta 2, and this is theta 1. So let's see, what does this say? This says when N1, just label that, N1 is greater than N2, then I am going to bend away from the normal. Away, with a Y, not a W, away from the normal. There you go. This is really important to wrap the brain around. And I think if you can hold on to it in terms of this definition, or just thinking of it in terms of the car, then for everything we're going to do from here on out, it's going to make sense. Because I can come back to here and think, okay, what's my light wave doing? Well, now when I make these things like convex lenses, because that's what we're going to do with all this, because you can't just make it cars and surfaces, or a concave lens, well, then we can think in terms of what does the normal look like and what's happening. My earrings, I need to put them away. What's happening with light as it hits these things, going from a higher index of refraction to a lower, or a lower rather, I'm sorry, lower index of refraction to a higher index of refraction going through a material. And the videos that I have following up on this do have much nicer pictures. He took time to draw them better than me. Okay, so that's the important thing going into Wednesday and Thursday. Then for our lectures, I will go into one of these examples, and we'll also talk about critical angles, about this thing called refraction and reflection, because the hint here is index of refraction. So pay attention to the videos this week, at least get a kind of understanding of how we're going to do some ray diagrams. So when we work through those, it'll make more sense. Challenge yourself to think of those ray diagrams in terms of what's going on here as far as light bending towards or away from, to kind of understand what would make light diverge or make light converge. And then the last thing to think about before Wednesday and Thursday is critical angles. So how much is being reflected? How much is being refracted? And that is it for now.